that it is. Yeah, so like this, the things are here. So x-axis, and if you consider this as y-axis, then range samples are y-axis. Then the vertical fellow is known as z-axis, so phase centers. So considering this, a plane wave, uniform plane wave on a linear linear antenna array, linear antenna array will be coming like this. So it is like normal to the array face is that particular angle, that whatever is being over here, normal to the array angle this is. And there are 0th element, first element, second element, dot dot dot, n minus 2 element, and n minus 1 element is here. And wavefronts, this is one wavefront like that it is coming. The next wavefront is coming and impinging on the second antenna. The separation between these two is the lambda here. Wavefront uh, separation is lambda, and these two antenna elements are separated by distance d. So the d is usually lambda by 2. It is multiples of lambda, and you can consider it as a lambda by 2. So D is usually. The signal at nth element is defined as yn of t. The yn of t bar is y bar subscript n of t is a e power j into omega is the angular frequency of that particular wave, and it is a complex exponential we are talking about, t minus nd sine theta by c. This is actually n is the number of antenna element number, d sine theta. What is this d sine theta? D is the separation between these two, and if you just see the separation between these two antennas is d, and if it is coming with some angle, if that angle is 90 degrees, then there is no problem. It is nd only. So sine 90 is 1, and then you will not have any issue of that one. Other than 90 degrees, if anything is there, that particular sine theta is multiplied with n and d, and then that particular value is known as uh, the distance that you will get over there. Equivalent distance. The equivalent distance by the velocity of light will provide you the time difference, that you will get at that particular this thing. Because of the phase difference, you will be getting a path difference. The path difference is leading to a time difference. That time difference is t dash. The t dash is nd sine theta by c, that is getting added to this omega into t minus t dash. T dash is nd sine theta by c plus phi naught. So this is your signal at nth element of the antenna array when the wave is uniform plane wave and array is linear array antenna. Okay, linear antenna is on a horizontal line. The antenna elements are placed. You know the array concept. So the sample yn of t of yn bar of t at every element at the same time is given like this. At the same time, if you try to go with a same time, that same time is a kind of snapshot. Snapshot means once you take a photograph at a specific time, then that is known as snapshot. So here also the snapshot is coming at this particular value at a t naught is a e power j into omega t naught minus t dash. T dash is this fellow plus phi naught. So if you try to algebraically rearrange this by taking e power j omega t naught plus phi naught as one term, okay, and then e power minus j nd sine theta by c as another term, then a e power j omega t naught plus phi naught will become a hat e power minus j 2 pi nd sine theta by lambda. So this will become c is equal to f lambda if I write. Then what this fellow becomes e power minus j 2 pi f, and then c is equal to f lambda. Ff get cancels, and then 2 pi nd sine theta by lambda. So this omega is written as 2 pi f. That f and c is equal to f lambda f is cancelled together, and then you will get this one. So assemble the samples into vector. Once you all these samples you arrange them in vector by taking n is equal to 0, n is equal to 1, dot 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 n is equal to capital N minus 1. You get this kind of vector is called spatial snapshot. Why it is spatial snapshot? Because my y of n is kind of taken from at a specific instant of time, but various elements, zeroth element, first element, and up to n minus 1 elements, what is the value of y at those elements are taken into a vector form, and that vector is a column vector. So this is known as a spatial snapshot. Okay. So far, any doubts for anybody? You can write all your doubts in the chat box. Then I will be answering them after some time. Then spatial, because there is no shortcut, dear participants, in this one. So beamforming, if you want to learn, you have to go through mathematics only, because I could have avoided this mathematics, but without mathematics, there is nothing to say about beamforming. Hence, I have introduced beamforming with mathematics here. So please try to listen this. The reference textbook that I followed is Mark Richards, Fundamentals of Radar Signal Processing, FRSP. You can refer and then go to the beamforming chapter and gain significant knowledge associated with this one. So this is like this. And then once you try to take the values of y of 0, y of 1 from the previous equation of this equation, then you will get all these values over here. A hat is still there. And then if you try to write k theta as 2 pi d sine theta by lambda, then a compact expression can be arranged here. Then a hat into as of theta. As of theta is called a spatial steering vector. Why steering vector? Because based on this theta value, the beam will steer. So a model of the expected form of the spatial snapshot for a signal arriving from angle theta. This is known as. It's a mathematical model of the expected form of the spatial snapshot for a signal arriving from angle theta. That is the spatial steering vector. So the terminology, I'll repeat it, what I have done so far. This is a kind of typical radar scenario where number of pulses are being transmitted, received pulses are sampled, and then various antenna phase centers are there. So for simplicity, a uniform plane wave impinging on a linear antenna array is considered here, where n element antenna array, n could be 8, n could be 16, n could be 256, n could be 1024, like that. So signal at nth element is yn of t is equal to a e power j into omega into t minus nd sine theta by c plus phi naught. The sample yn dash of t at every element at the same time is known as a spatial snapshot, that is represented using this equation. A e power j omega into t is replaced by t naught, and upon algebraic simplification of this one, a hat is introduced, where a hat is a e power j omega t naught plus phi naught, and then e power minus j omega nd sine theta by c. So n is equal to 0 to n minus 1. Assemble the samples into a vector. So y is equal to y naught y1 dot 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 yn minus 1 transpose. This vector is called a spatial snapshot. And then upon substitution of all these values, you get this one where k theta is replaced by 2 pi d sine theta by lambda. So where a hat into as of theta is called a spatial steering vector. This is known as a mathematical model of the expected form of the spatial snapshot for a signal arriving from angle theta. Okay, so that is what it is. Beamforming means forming a weighted sum of the snapshot samples. What is snapshot? Snapshot is this y, and steering vector is there, and a hat is also there. For that, why, if you try to take a kind of H transpose, where H transpose is a vector of complex weights, you can also consider that as a filter also. That is what is our FIR filter that we spoke about earlier days. So H naught H1 dot 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 Hn minus 1 whole transpose. Z is a scalar output of the array for a single time instant. Z is a scalar output, because once you multiply this one, you will get a scalar output of the array for a single time instant. At this single time instant, what is our value? So then it is like a aside, is like just we are trying to understand the Hadamard product. So it is element by element multiplication of two vectors is known as Hadamard product. So when a naught a1 an minus 1 is there, b naught b1 bn minus 1 is there, how to multiply them in the, not in a vector form of matrix multiplication form, but in a kind of Hadamard form, element by element multiplication is known as this one. In MATLAB, this is known as star into dot into star. Then let us see what is known as spatial filtering. Spatial filtering is beamforming is coherent combining of signals from multiple phase centers to provide selectivity in angle of arrival. So we will be trying to get the selectivity in angle of arrival. I will show you practical experiment that we have done at our startup uh, in the NITK. So that is to form an antenna beam. In Doppler processing, we have temporal samples, one receiver, one range bin, multiple samples. That is what is Doppler sampling. So that you don't bother about it. Now we have one range bin, one slow time sample, but multiple phase centers physically distributed in space. This is known as spatial filtering. So beamforming definition is this: coherent combining of signals from multiple phase centers to provide selectivity in angle of arrival. So spatial filtering is one range bin, one slow time sample, but multiple phase centers. So conventional beamformer is you choose weights in such a fashion that W naught, W1 e power j k theta dot dot Wn minus 1 e power j n minus 1 into k theta. So previously what was my this thing minus j k theta. So minus this one. So now what is that we are trying to get here plus jk theta, so that eventually you will, when you try to multiply them, you will be ending up with this as Hermitian theta will come, this weight vector, and H is formed as Hadamard product of steering vector to select preferred AOA and amplitude weight vector W to define main lobe or side lobes. So you go with Hamming window, Taylor window, antennas concepts. Those who knows, they can understand the window concept, the windowing of the a kind of beam pattern and to obtain a desired beam pattern and all that. So we say weight vector is steered to an angle theta in this one. So when you do that one, so when this jet, whatever the Hadamard product is there, and then H is chosen. After H is chosen, where was H? Z is equal to H transpose Y. We spoke so far about H. After obtaining H, you try to put the H into this Z. So Z of theta is H transpose Y. And if you try to rearrange this fellow, it will come like this, where omega w is a vector of all ones, and then like this you will get z of theta. You can write like this: when you sum and all that, it is like sine n into pi d by lambda sine theta minus theta naught. Like this kind of format you will get. So array pattern for n is equal to 11, 11 elements you take, and theta naught is equal to 30 degrees with uniform weight and Hamming weight. This is how the beam pattern look like. Normalized array response when you simulate, try to do that one. So uniform weights is like this, but when once you window it, side lobes will be reduced, but main lobe will spread. That is what is the kind of concept that that will come into picture. So the green color is Hamming windowed response of the beam pattern, and the blue one is uniform weights of the beam pattern. So matched filter for beam forming, if you just look at like this now, these results can be obtained using our vector matched filter, these results. So there is a vector matched filter that you need to understand. So how vector matched filter is there and all that, that I am not trying to cover in this short class of 1.5 hours. So we want to maximize, I will take only 1 hour 15 minutes only, because that is sufficient with this mathematical rigor. So let us only focus up to 1 hour 15 minutes. So already we passed the first 20 minutes of the lecture. So up to 7:15 I will take, because I waited some time before you come. I came at 5:55 and you people didn't come. So these results can be obtained using our vector match filter. So we want to maximize the signal to interference ratio in the output z of theta when the desired signal is a plane wave from AOA theta and interference is white noise. So target model is just T is equal to AS of theta. Interference covariance matrix is just SI is equal to sigma n square I. This is how it is. Interference covariance matrix is I is identity matrix here. Sigma n square is variance of that additive white Gaussian noise. So with that, W is H weights is SI inverse into T target. Since T target is known to us, the optimum filter, this is SI inverse is the Wiener filter coefficients actually. A Wiener filter coefficients is interference matrix inverse into T dash, T Hermitian. So the 1 by sigma n square AS Hermitian, AS of theta Hermitian, because T is my AS of theta. That is what I assigned like that. So AS of theta is known to you. You write that AS of theta, and the Hermitian is complex conjugate of complex conjugate and the transposition. If you do, then that is known as Hermitian. So you have to perform complex conjugation to the AS of theta and the transposition. So if you do that one, then it will come like this. So z of theta is H transpose Y. So Y is anyway here like this kind of term. And then if you look carefully, this one, H transpose Y equation. So then it is like H transpose Y is given in a form of n is equal to 0 to n minus 1 yn of yn e power j k theta n. This is how my z of theta looks like based on my previous this thing z of theta. Yeah, H transpose Y is like this. So that one is rewritten over here. That one is rewritten over here in a discrete way, and then k, this one is like this, equivalent to minus k theta. So antenna pattern looks like a discrete time Fourier transform in this case. It is like a discrete time Fourier transform equation. It looks like of the data snapshot. So that is one module. So next module in my this thing is adaptive beamforming. So so far any questions from anybody? I am only presenting myself. Any questions in the chat box? Nobody has asked any question. Your faculty, sir, you have to
Till
ask
now,
some questions. No
till now,
questions.
no questions in chat box, sir.
No
Till now.
questions is not excusable. Please ask some question,
Okay, sir.
professors.
Fine.
67 participants are there. You can orally ask, you can also write over here.
Okay, sir.
I just did some very difficult math there, so you must ask what is it.
Okay, sir. Fine.
So first half an hour is almost done. So please ask. Let us have some discussion. Then I will go for adaptive beamforming, because these concepts are widely deployed in what is known as 5G. What is 5G? Massive MIMO. What is massive MIMO? Number of transmitters 32, 64, 128, 256, cross 256. Those many transmitting and receiving antennas are present over there. So please ask some questions. because beamforming may be there in many places. The title, whatever title that you put is like only I have taken half of it because smart antennas and the beamforming, adaptive antennas, such kind of thing. So adaptive, we will talk about adaptive. Why we multiply interference matrix? Because that is what very good question. Thank you. So before I go into this one, see why we multiply interference matrix. So beamforming topic is here. So there was some assumption, no, that we have taken. What was the assumption that we have taken? See here, we want to maximize the signal to interference ratio in the output z of theta when the desired signal is a uniform plane wave, AOA theta, and interference is white noise. Because without interference, you cannot detect a signal, no? So I'm trying to get the signal from the noise. So that's why interference is considered here. Once the interference is considered, you must model the interference related covariance matrix. Without getting the interference related covariance matrix, in the presence of interference only, you are trying to detect a signal. That is why the optimal filter coefficients are obtained SI inverse of T Hermitian. So that is why we have done like that one. So without having the modeling interference, here it is considered as white noise. In case of sonar and such kind of places, you cannot consider the interference as white, it is colored noise. Then the business is different there. So you have to go, because as far as radar is concerned, in general, we try to communication and radar, we consider additive, white and Gaussian distribution. So that white noise Gaussian distribution is considered here. That is why SI is modeled as sigma n square I. That sigma n square I is taken into consideration, and then optimal filter coefficients is always like SI inverse into T dash. This is a Wiener filter solution. I have not done this one. So Wiener filter solution, Wiener filter is considered and obtained the filter coefficients. After obtaining H, Z of theta is computed from H dash and H transpose and Y, and the equation comes as a DTFT kind of equation. Is that fine? So whoever has asked, Serenya D. Thank you so much, Serenya, for asking that question. So that is what is the answer. Any other by anybody? You please ask something. Generally, we do beamforming to increase SNR. In what way conventional beamforming different from adaptive beamforming, sir? Okay, so conventional beamforming, because conventional beamforming is the one which I just mentioned, because steering vector. Yeah, thank you, Saranya, for that. Thank you. So this is Imran Khan asked me. So we generally, you see, the question is a little complex. So let me simplify this one. So generally, beamforming is about, as I mentioned, you are trying to get the antenna pattern when the wave, uniform plane wave is impinging to you on a kind of, without an array normal, then you know what is that angle kind of thing. So sine theta is equal to that 90 degrees. So you will not get any kind of problem over there. But when it comes to that sine theta, the d sine theta by the d sine theta difference that you get is the one which is coming to you as a kind of parameter to tune the direction of the beam which is coming. That is what is also known as angle of arrival. So in that, what we are actually trying to do there is, it is like we are trying to get into the conventional beamforming. We are defining this whatever the coefficients that are there by Wiener filter solution, and then brought it those coefficients. Optimal filtering, that is also conventional beamforming, is not a small one. We obtained them. So later, in the case of this adaptive, because there we assumed the Gaussian noise as white and other kind of thing. Later, we try to adapt these coefficients based on some learning algorithm. So adaptive antennas and then adaptive signal processing originally originated for adaptive beamforming only. So adaptive antennas. So people wanted to steer the beam by using these weights. So those weights are computed by using a simple least mean square algorithm. Again, this leads to what is known as different from adaptive beamforming. No, this is completely different from the conventional beamforming, because here we are trying to get the, because Wiener filter solution only, it's like minimum mean square error estimate only, but we are trying to do that with the help of a least mean square algorithm and various other algorithms. So we are trying to minimize the thing, and later on the minimum variance distortionless beamformer. So in that also various modifications also have come. It is like adaptive beamforming is the one which people are trying to put it in much more this thing. But Wiener filter solution also many a times difficult to get. So there also we are not trying to adapt those coefficients. We try to determine, but in kind of STAP, space-time adaptive processing. In generally, it is applied in radar and sonar. In such cases, the beam steering is applied and then try to get those coefficients, and those coefficients are used to shape our beam actually. So that way, it is like SNR, our maximization here, it is not only SNR, communication terminology, SNR is the idea, but in radar, sonar and other places, it is always SIR, signal to interference ratio. There, Y interference is noise plus clutter will come into picture. Noise plus clutter plus intentional interference plus unintentional interference. So all these things put together is known as interference there. So intentional interference is known as jamming. We will see those jammings and how people solve this jamming problem with the help of adaptive beamforming. So is that okay? Can I go forward, or any other questions are there from anybody? Please ask couple of them, because that will give you more idea of what is all about. This is a ATAL FDP. So I have accepted to give this lecture. So it has to be as much user friendly as possible. So Imran, am I fine with that, my answer, or do you want more explanation for that?
Fine, sir. Fine, sir. I completely
Okay.
understood, sir.
Yeah, thank you. And then any other questions from anybody? Imran Khan is the organizer. Saranya is a kind of, faculty member, female faculty member. So we need now one male faculty member to kind of ask one question at least. There are around 72 participants.
Sir, what is the
One
difference
more
between
question,
adaptive
then
farming
go
and
forward.
hybrid beam farming,
Which
sir?
one?
Adaptive beam
One
farming and
question.
hybrid beam farming, sir.
One question. You please write it, because that is better. Others also can see if you write the question.
Okay, sir.
Anything is there? Nothing is there. You please write, and I will come back and answer also a little later. So let me go and do the lecture. All right. So here is my slides being presented. Okay. Okay. Somehow, 1 minute. Okay. Just trying to go into the tab. I'm unable to come. Okay. The full screen mode I can come only with the help of. 1 minute. Let me go back to my original presentation screen. Okay, let us see adaptive beamforming now. Okay, so in this adaptive beamforming, because jammers actually I mentioned about, just now I mentioned about the in general interference in any scenario is, especially in the kind of sensors, radar, sonar, such kind of scenario, there is one kind of thing known as noise that we modeled as additive weight Gaussian noise. Then there is a jammer. This jammer is known as intentional interference. Unintentional interference is nothing but some people are there for their own purpose, and then they try to radiate emissions which is unavoidable. Sometimes if it matches with the same frequency, you will caught up with the interference. That is known as unintentional interference. Then the next one is clutter. Clutter is unwanted returns coming from the vicinity of the target. When the target is present at some place, then when the clutter is there, those returns also you will get it. Jamming signals arrive at the antenna from a specific angle of arrival. Jammer waveforms can be noise-like or radar waveform-like in general. So can also have in-band interference, interfering signals at some radar frequencies from cellular services, public safety services, television, etc. Jammers can be much stronger than radar echo signals because they only radiate in one direction. They only propagate in one direction. Echo has to travel two-way propagation loss. So they hence jammer signals are much more stronger than the regular signal. So frequency allocation. Jammers relative to array. So you can see there are one side lobe jammer, one main lobe jammer we considered. When main lobe some interference is coming, that is main lobe jammer. Side lobes interference is coming, antenna side lobes, the side lobe jammer. Here, both are side lobe jammers are considered, one at plus 18 degrees, other one is minus 80, minus 33 degrees. So n is equal to 16, antenna steered to 0 degrees, side looking, and then no amplitude weighting is considered here. Weightings or side lobe reduction is one way to reduce jammer power of the output. If you reduce side lobes, then jammer power also will reduce. That is one way to eliminate the side lobe power of the jamming. But what we can do is now match filter for adaptive beamforming. So if you can apply a vector match filter to the problem of choosing beamformer weights to maximize output to signal interference ratio. So vector matched filter, because anybody fully aware of matched filter concept? So if you are not, then please tell me, because this is the time to talk about matched filter. Please tell me, then I will go. So at least if you write you want matched filter to give you some idea of matched filter to you in this class, or you are fully aware of matched filter. So can somebody write over here? 72 participants are here. So if you write somebody, then matched filter, I'll explain 5 minutes matched filter. You already know fully about matched filter. It provides maximum SNR. How it provides and where it is applied. Anybody aware fully? Or you want me to teach? Tell. Not teach, not fully. I cannot derive the equation, but I can tell you. So matched filter is like, is an optimal filter. So this is actually designed to maximize the signal to noise ratio. We call 2E by N naught and all that. But in general, that is the end expression of SNR. But in general, what is happening? No, the impulse response, we usually assume that as an LTI system. The matched filter is an LTI system, and we consider the impulse response of the matched filter is time reversed, time delayed, scaled, complex conjugate of the incoming signal. So that is the beauty there. So one is time reverse, other one is time delayed, complex conjugate, and scaling. Upon doing all that, so you will be matching your impulse response with the filter, except that when you go into frequency domain, you will come to know except the time delay and the scaling and complex conjugation and time reversal, it is exactly the kind of incoming signal. So therefore, when you go into the Fourier domain, you can see multiplication of these two signals will give you magnitude square of the incoming signal. That is what when you go into y power j omega is equal to h e power j omega into x e power j omega, you will get like that. So magnitude square of x e power j omega into exponential of that delay term that you will get. So that way it is going to come, that magnitude square of that incoming signal is the input signal power energy that you can consider. Energy in time, energy in frequencies, Parseval's energy theorem, you equate and get the E, and whatever the power spectral density power that you get in the denominator is n naught by 2. That n naught by 2 is like 2E by n naught it will come. So that is how, and it is widely deployed in radar for pulse compression, and also widely deployed in sonar for pulse compression, and it is extensively used in communication receivers for the optimal signal to noise ratio. So it finds a wide range of applications because matched filter is a very most popular and widely used filter. So with that, we can go to the adaptive filter. Adaptive, this thing, vector matched filter. There we have considered only scalar this thing. We are now going to vector matched filter actually. So the vector matched filter is the one which we are talking about. So let us see vector matched filter, where I'm not unable to explain fully to you the vector matched filter, but you can gain some. You can later on look at the Mark Rich's textbook to understand the vector matched filter. So let me see. After exiting in full screen mode, again to go back to full screen mode, I have to go to this one anyway. So we can apply the vector matched filter to the problem of choosing beamformer weights to maximize output signal to interference ratio. Interference is now noise plus jammers. That is what is noise is here. Unintentional interference is ignored. So only two jammers are there, J1, J2, like that kind of this thing. Independent jammers are assumed to be independent of noise and each other, and also they are independent of each other. So interference is always additive in nature because they are not dependent. And the jammer, this thing, steering vector, you can write like this in the similar to that of the previous this thing. But one weighted, the WT is zero mean and unit variance weight random process. This is because you model like that. Spatial snapshot of that is looks like this, and J is coming like this, and then you take the steering vector and then you estimate the jammer, covariance matrix of the jammer, estimate it, and find the S Hermitian, and find the weight vectors associated with this jammer. After weight vectors associated with this jammer, you will nullify them because plus 18 degrees minus 33 degrees now, because you have estimated it properly and kept null in that direction. So antenna pattern now has deep nulls at both jammer locations, at both jammers angle of arrival locations. You estimated their angle of arrivals and the jammers are cancelled. So this is what is the beauty of this adaptive beamforming. So then distortionless beamformer is another class of that. Distortionless beamformer is another class associated with that one. So you can refer MVDR beamformer, Kappan's beamformer, such kind of thing. We actually worked with variations of that with real data. When interference is noise only, peak voltage gain, steering direction is AS of theta, and output SIR gain relative to single element SIR is a factor of Sn. When jammers are present, both are reduced somewhat. Distortionless beamformer guarantees gain in steering direction remains constant. That is another beauty of distortionless beamformer, guarantees gain in steering direction remains constant. So that H comes here, not only this one, but there is one K, that K has to be estimated from these values and then put forth that K into the H, so that it always guarantees the distortionless beam forming. So jammer in main lobe is another example. When main lobe jamming is there, what to do? Minus 2 degrees and 30 degrees. Minus 2 degrees is the main lobe jamming. 30 degrees is side lobe. So how to do this one? Main lobe peak is severely degraded, pointing error. So double peaks are present because of this one. Jammer is there, two peaks are there. We don't know which is main lobe, which is side lobe in this case. So you go with the procedure and then try to nullify those values. So then up to that is fine for you. So I will be now moving to some of our own experiments. So this is Zoom platform. I usually does not like to present some of our innovations in the Zoom platform, but however, this being a lecture, could have gone for some other kind of thing. Anyway, let me look at what we have done with respect to this. A lot of experiments have been carried out, but specifically some experiment, drone detection, we carried out some certain experiment. This is actually, we published a paper also. When drone is there, there is one radar sensor, we purchased it from TI with the help of some other guys. So it is like, uh, okay, so it is like drone and the AWR2243 sensor and then DSP EVM and processing the complex data in MATLAB and implementation of music algorithm and find the DOE. Multiple signal classification algorithm is the music stands for. That we have implemented, and this is with real data. We collected 13.43 is one angle of arrival and 11.5 is another angle of arrival. So both are using this one micro drone detected at these locations. So there is another experiment which we carried out at our entrepreneurship park with a transmitter at regular band and a receiver with four element antenna linear fashion. We arranged it. It's not a perfect antenna, but still we could able to radio. This is from a transmitter, this from a receiver, and we collected real data. That real data we did music. We also estimated using Spirit, that is a Spirit estimation of signal parameters via rotational invariance techniques, then minimum variance distortionless beamformer and its variants, then correlative interferometry. These are most popular, widely used one is fourth one and MVDR also. So this is the table that we obtained for various ground truth values, and then you can see MVDR, covariance interferometry, optimal MVDR, robust MVDR is giving significantly better performance compared with the other algorithms with the ground truth values. So this is what is our observation. So I think this is the lecture. So you want any further things on this one? So we will try to because I have nothing more to teach actually. So if you have any questions, I will answer. Then another 10-15 minutes we can have some discussion. So please ask some questions. So anything that is relevant to you or not relevant to you also, you can also ask questions. Anything? Already all questions are asked, sir. Nothing more now. Because I am not exactly from communication background. I'm from a sensor background, so therefore. In microphone array processing, Microphone array processing. How does distortionless beamforming enhance speech while suppressing noise? Okay. So in microphone array processing means you are talking about maybe, yeah. So it is like whatever I know. How does distortionless beamforming enhance speech while, so you are talking about speech, okay, while suppressing noise. So as I mentioned, that that scaling factor we are estimating, then the distortionless, after collecting data, can we steer the beam to the particular directions for adaptive beamforming? So obviously, because that is what is happening, no? So after collecting data, can we steer the beam? No, no. Whatever the direction that is coming, only because usually in kind of radar, you try to because whatever the direction that is coming in receive, you will be able to form the things, and then receive beamforming is also there. You can try to look in that direction, but generally when you transmit, the beam steering concept is applied. That beam steering is like whatever I told you, based on the phase uh, difference, the path difference will come into picture. That path difference will induce a this thing, because based on the path difference, phase difference will come. That phase difference actually will steer the beam in the transmit side. In the receive side also, in similar kind of thing only it will happen. Microphone array processing, because generally the microphone array processing happens in many places. One is sonar. Lot of processing happens in microphone based, because they go with very highly acoustic sensors to get the uh, kind of data from other, especially submarines, and then other kind of thing, other underwater bodies. They try to get the data using this microphone array, because they are acoustic signals basically. They are not exactly speech. Speech is human speech, is around 300 to 3.4 kilohertz. That is a very small range of signals. So there, because the same concept only, the distortionless beamformer will do that, but generally in speech and other cases, there is acoustic noise cancellation has got a lot of adaptive other adaptive based algorithms, not the MVDR, such kind of things, but other algorithms are known as LMS, and its variants are widely used. LMS, up to how much distance jammers will work effectively? That is a very big question. So I'll come to that one. The microphone thing, let me explain whatever I know. So microphone adaptive noise cancellers are there. You go now, there is one company known as Marshall. There is another company, Bose. You try to get their kind of Sony. They try to get their high-end kind of the audio processing equipment, audio speakers. So for example, what they say is literally there is no noise, even though in the original source noise is present. But when you hear from our own sensor, our own output from the speaker, you will not be getting. So that they use what exact technology is not known to anybody, but what they are using is they are going with a lot of adaptive noise cancellation techniques. So there is a whole range of adaptive noise cancellation topic is presented both in hardware and software by Professor Mrutyunjay Chakrabarty, Adaptive Signal Processing, NPTEL videos. You can get some very significant idea of this adaptive noise cancellation. There are many professors who worked in that domain. Professor Ganapati Panda of IIT Bhubaneswar, former professor. So this Mrutyunjay Chakrabarty also still in IIT Kharagpur. You can see his video lectures on adaptive signal processing. He focuses more on this adaptive noise cancellation. So mainly based on LMS and RLS actually. They are recursive least square and least mean square algorithm. So MVDR based things, I am not fully aware as far as speech signals are concerned, but people might use also in microphone array processing, that I am not fully aware. Then after collecting data, can we steer the beam to a particular direction? So before collecting the data only, in the receive beam forming, generally we will try to look for, uh, because by adapting my receiver filter coefficients, whatever in software form, I try to, because when I have multiple antennas, I try to I try to look in certain directions and then see where my echo is coming, such kind of thing. But after collecting the data, we are not able to, that is, we will not do that. Generally, we will not do that for adaptive beamforming. Adaptive beamforming also, simultaneously while collecting data only, we try to steer the beam both in transmit and receive and then do it. As far as jammers is concerned, it is a very big game actually. So generally there is a stand-off jammer, self-screening jammer, barrage jammer. They are all come under the class of electronic countermeasures. So generally, when you radiate a high power, then larger distance you can travel, and then to radiate a high power in a real scenario, it is extremely difficult. So, and sometimes when you try to jam, enemy receiver knows that you are trying to jam, then they will go for electronic countermeasures. So in that case, how effective you play with your jammer is a very difficult task and highly classified information. Nobody knows what exactly happens in real scenario. The electronic support measures, electronic warfare is a very big subject. How much distance jammers will work effectively? So that is $1 million question. Practically, I cannot tell any information about it because I do not know. And whatever I know is theoretically you can model and see how much distance effectively you can put it based on radar range equation based jammer range equation. So based on that, you can try to, because it is always inversely related to r square rather than r to the power of 4 because of one-way travel. Power density, jammer power density at a distance r is pt by 4 pi r square. It is not two-way travel distance. So that is how I mentioned. Based on that inverse square relationship, you can estimate how much distance that it also depends upon spurious free dynamic range of your receiver, the enemy receiver. So that is known as SFDR, that is minimum detectable signal, and the maximum signal where you will be spoiling their receiver. So based on that, you can calculate and then estimate how much distance it effectively goes. So any other question? Thank you for asking these questions. Any other questions by anybody? So if there are no questions, then I think 9:06 now. Another 5 minutes we can do something. Hello. So far, very good questions is asked. One new message. Let me look at it. In what way high-speed communication can be achieved using beamforming, sir? So very good question. So it is like high-speed communication. Made a massive MIMO. So maybe Imran Khan only. Okay, sorry. Okay, thank you. Massive MIMO is one. This thing, the high, the speed. In communication, the speed is bits per second. How many bits per second? You go back, if you are around 40 years old, you can estimate. 30 years old, we were trying to get the 256 kbps, 64 kbps, 128 kbps was our data rate. And hardly anybody is getting internet those days with only for email and other thing. Multimedia communications is ruled out. mobile data-based multimedia processing like WhatsApp and Facebook and other kind of things is also ruled out those days. So what was happening those days is like completely speed limited. Thereafter, what happened? Thereafter, high gain antennas came. Then the bandwidth is enhanced based on the innovations that happened over there, and the 3G came, and the 4G also came in. 4G itself, the MIMO communications have been introduced. The speed in MIMO, because when multiple antennas present, only beamforming is possible. So, and also not only high speed, multi-user communication. Multiple users are being catered by using same cell site in this one. Multiple users are being catered by using same cell sites, and we have been doing that effectively with our kind of processing. And especially 128 by 128, 256 by 256 massive antennas are present. So you can extremely, they are all like, you can steer the beam electronically with very high precision. Therefore, you can able to achieve what is normally possible with our own kind of 1 minute. So charging is getting, yeah. So that is otherwise is not possible. Is like happening these days with the help of so very less battery is there. That's where I am. So anyway, so if you have because that is possible because high speed is achieved because earlier we had the spatial beam forming spatial only, the beam forming is based on these antennas you are trying to go with earlier TDMA, all this kind of thing concepts are there now. Because of this multiple radiating antennas, you can achieve that high speed, desired high speed. Any other questions? Still now 87 participants are there. So maybe anticipating for next lecture because this is boring with lot of mathematical equations. Okay. Any other question, Imran? Is that fine, or should I? Uh, if any other questions are there, I'll take. Otherwise, this is a short and sweet lecture. Let us close this now. Yeah, yeah. Okay, thank you. So if there are no questions, then I'll close at this point of time. Then we may meet in some other occasion. Thank you. I felt very happy with the number of participants is around 86 at this point of time, and an evening of Thursday evening in September month. So thank you, Imran, for providing me this opportunity. So
It's my pleasure, sir. Thank you, sir.
since I avoided formal introduction and all that, so we saved some 5 minutes time. I'm
Yes.
exiting. My battery is draining. It's only 4%. Let me conclude and close the session. Is that fine now?
Okay, sir. Okay, sir.
Okay. Thank you, Imran. Yeah. So I'll be exiting. Thank you.
Thank you very much, sir. Thank you, sir.
Thank you.
Thank you, sir.
Dear participants, thank you for your active participation. Feedback link for session 7 is available in the chat box. You please fill it.
Balma Buje. Balma. Hello, madam. You are ready, madam?
Yes, sir.
Shall we start the session, madam?
Yes, sir. We'll start.
Madam, before we start, madam, let me introduce about yourself, madam.
Yes.
I am going to introduce about yourself, madam. I am going to introduce, madam.
Yes, sir.
Good evening to our respected principal of St. John's College of Engineering and Technology, Dr. K. Sudhakar Garu, our EC Department HOD, madam, Dr. K. Suvarna, madam, Program Coordinator CP Imran Khan Garu, esteemed faculty members and participants of this faculty development program. On behalf of SJS at EC Department Organizing Committee, it's my pleasure and honor to extend a warm welcome to all participants to the second session of today's program. Today, we are privileged to have with us a distinguished resource speaker, Dr. Chintara Vijayadurga, who brings with her a wealth of experience in 5G or 6G communication systems, the role of AI and IoT in smart network management. Now, let me give a brief introduction about our speaker. Dr. Vijayadurga Chintala is an assistant professor, senior grade in the School of Electronics Engineering at VIT Velur. She earned her PhD in wireless communication from NIT Warangal and has over 15 years of teaching experience. Her research focuses on RF wireless systems, a visible light communication, optical wireless communications, and next generation 5G or 6G technologies. She has also contributed 11 publications in reputed journals and conferences, highlighting her commitment to advancing knowledge in her field. We are confident that her session will provide valuable insights and immensely beneficial to all of us. Thank you, madam, for giving this opportunity. Please continue the session, madam. Thank you.
Okay, sir. Good evening, everyone. I'm delighted to be here today as a part of this FDP. I thank the organizers for inviting me. We'll start the session.
Yes, madam. Start, madam.
Is it fine, sir?
Yes, madam.
Is it visible?
Visible, madam. Please keep full screen, madam.
Is it okay, sir?
Now it is okay, madam.
Okay. Right. So today I'll give a lecture on 5G or 6G communication systems, role of AI and IoT in smart network management. So the main theme of this session is integrating intelligent technologies to provide an access to the efficient network operation. So what is meant by intelligent technologies is nothing but here artificial intelligence, Internet of Things, and 6G technologies. If we integrate all these intelligent technologies, it offers an efficient network operation. That means it can provide an improving throughput, less delay. Everything is smart. Nowadays, everything is smart, smart cities, smart life, that means smart home, everything to be smart because of these integration of all these technologies. We'll see in detail. So first we'll discuss about introduction to wireless communication evolution. So you know very well, so it can start from 1G. 1G offered a basic analog communication. It uses the frequency modulation and frequency division multiple access. So it can provide only voice communication. There is no SMS messaging, internet, it's not there. So to get that services, we'll go to the 2G. The 2G is provides the digital transmission only. So digital transmission and SMS messaging. So it is the first technology, especially for 2G, we are using GSM global system for mobile. It provides the digital transmission and SMS messaging, but reduced errors when compared to the 1G and provides high data rates also. And coming to the 3G, 3G brought mobile internet to our life and multimedia messaging. Here we are using the CDMA technology, that is code division multiple access, which is better when compared to the FDMA and TDMA. And coming to the 4G, the 4G has created a revolution in the wireless communication due to the use of OFDM. OFDM is nothing but it is orthogonal frequency division multiplexing. As the name implies, orthogonality is there, and then frequency division multiplexing. It is very simple and offers high data rates and robust against fading, better spectral efficiency, and it is a multi-carrier waveform. That's why you can provide access to more users, and it provides the enhanced speeds supporting HD streaming also. Then why are moving from 4G to 5G? 4G is very good, but why are moving from 4G to 5G is nothing but due to the rapid growth of exponential growth of these mobile devices. Everyone is using mobile devices, and internet comes into our life. So we need to provide access to all the users and provides high data rates. So to get the high data rates, we'll go to the 5G. The 5G provides mainly 3 services. One is enhanced mobile broadband service. As the name implies, it can provide enhanced mobile broadband service. That means provides high data rates. And this 5G operates in the 2 frequency ranges, FR1 and FR2. FR1 operates the 450 megahertz to 6 gigahertz. It is also called as the sub 6 gigahertz band. Coming to the micro millimeter wave band, that is FR2, frequency range 2, it is called as the millimeter wave band. It can operate at the 27 gigahertz to 57 gigahertz. So due to these high rates, it provides the high data rate. High frequency, it provides the high data rate. And then the next one is the massive machine type communication. As the name implies, massive is nothing but more number of devices. Around 1 lakh devices we are connecting. 1 lakh machines can be connected. So that is the beauty of 5G. And then because of this, it can provide enabling smart cities and autonomous vehicles. And the third one is ultra reliable low latency. As the name implies, it can provide the reliability, high reliability, but low latency, that is around less than 1 millisecond it can provide. So that is the beauty of 5G. And coming to the future technologies, that is 6G has many applications. 6G will provide very high data rates when compared to the 5G, around terabits of the data. So that's why the 5G, the 6G operates sub-terahertz communication and terahertz communication. Around 100 sub-terahertz is nothing but it is 100 gigahertz to 1 terahertz. And then terahertz communication is nothing but it is around greater than 300 terahertz. Something, if you take optical wireless communication or visible light communication, it can operate at the greater than 300 terahertz. Then in 6G, one more important topic is AI, artificial intelligence. It is integrated. 6G plus AI almost provides immersive and intelligent experiences. And then quantum communication, quantum security is mandatory. So nowadays, the main problem, because everything is technically we are growing, but there is a chance of the security is very, very less. We need to provide a security that is possible because of the quantum. Then technological, what are the technological foundations of 5G and 6G? We'll see. So here, this indicates connecting the world. So basic mantra of wireless communication is stay connected anywhere, anytime. And that too here, digitally we are connected and smartly we are connected. So that means here, mainly we'll discuss about 6G applications. So 6G enables holographic communication, digital twin technology, and immersive mixed reality experiences transforming digital interaction. So here main thing 6G applications, if you take a hologram technology, it uses the laser light and provides the 3D images. So these are all technologies mainly entertainment purpose one side, and the other side smart health monitoring systems. This is very, very important. Health is very important. So one side entertainment purpose and second one is technological, that is visual classroom lectures also we can give, that is one side, and the next side is that is mainly health monitoring systems. So we can treat effectively using this holographic technology. And coming to the next one is digital technology. As the name implies, digital twin is nothing but it creates a virtual replica of a physical object, whether it is a person, system, or process, anything, connecting real world data to a digital model. So for this digital technology, if you integrate a data from the IoT, cloud computing, edge computing, AI, these digital twins enable better informed decisions, streamlined processes. It can be used in many fields like manufacturing field, engineering field, urban planning, and in many applications, this digital technology is useful. So these are the basic 6G applications. There are many applications are there, but technology-wise, I have taken these two. And then I'll discuss about 5G waveform candidates. Here mainly coming to the 5G. Why you are going for 5G? Okay, if you take a 4G, OFDM is used. In physical layer, we are using the OFDM, that is orthogonal frequency division multiplexing. It is very robust against fading, but it suffers some drawbacks. What are those? First one is the out of band radiation. That is the main drawback. And one more thing, synchronization. Synchronization is mandatory in 4G. So when you are coming for 5G, if you want to provide a massive machine type communication, you need to connect millions of devices. So providing synchronization for them, it is very, very difficult. So that's why OFDM maybe some insufficient for this 5G technology. So that's why they are changing from OFDM to filtered OFDM to eliminate this out of band radiation. And other than that filter OFDM, there are many waveform candidates are there. So the first one is the GFDM, that is called as the generalized frequency division multiplexing. In this, all 5G waveforms are the filtered waveforms because if you take a OFDM, all the subcarriers are filtered at a time. So that's why it provides out of band radiation. That is the main problem. Because of that leakage is there. So to avoid that drawback, in 5G, all the waveforms are the filtered waveforms. Here in GFDM also, a prototype filter is employed to each block, which eliminates out of band levels. But the drawback of GFDM is to eliminate the self-interference, we need a complex algorithm. So computational complexity is very high. So for that one, we'll go for FBMC. FBMC is nothing but it's a filter bank multiple carrier. As the name implies, filter bank, the bank of filters are used, and it's a multiple carrier. Okay, so here, as the name implies, it employs per subcarrier filtering. That means if you want to use a 256 subcarriers, so you can use a bank of 256 filters. That means for each subcarrier filtering, each and every subcarrier, we can use a filtering, which reduces out of band emissions effectively, and intercarrier interference also eliminated effectively. But the problem is because of this narrow band frequency response, it needs a long filter length. Again, complexity is very high. So, and because of this one, it is not suitable for IoT and short burst communications. So then to eliminate these drawbacks, there is a solution, that is UFMC as the possible solution for 5G. UFMC stands for Universal Filtered Multi-Carrier System. As the name implies, it is universal. So it is better when compared to GFDM, FBMC, and OFDM. We'll see about the UFMC system. So Universal Filtered Multi-Carrier is an alternative to both OFDM and FBMC due to UFMC is simple like OFDM and robust like FBMC. In UFMC, the total bandwidth, the entire bandwidth is divided into subbands. Each subband contains consecutive subcarriers. Because in FBMC, for each and every carrier, we have employed a filter. But instead of using that for every carrier one filter, here in UFMC, we can divide a band into a subbands. Each band consists of the number of subcarriers, and for subband we can use a filtering. That's why it is called as the sub-band filtering. UFMC system employs a sub-band filtering unlike FBMC. Hence, it does not require long filter length. As well as we are using filters, especially Chibishu filter is used, it can eliminate the out-of-band radiations effectively. So UFMC can be suitable for short burst communications and IoT. So that is the beauty of IoT. So it can integrate with IoT. Okay, then one more thing, the spectral efficiency of UFMC is very high when compared to the OFDM. Why? Means it does not need the cyclic prefix. So because cyclic prefix eliminates the ISI in OFDM. Here, without cyclic prefix also, we can eliminate ISI. So that's why there is no need of spectral efficiency, no need of cyclic prefix here. So the spectral efficiency of UFMC is high when compared to the OFDM. And one more thing, main thing is relaxation to carrier frequency offset. This is a very, very important thing because the OFDM suffers with this carrier frequency offset problems. Are the attractive features of UFMC system. Then this is the transmitter structure of UFMC system. I have already explained. Total data is divided into subbands. After that, we can implement a mapping. That means you can use modulation techniques because it's a digital technology. So you can use either phase shifting techniques or quadrature amplitude modulation. You can use any modulation technique. After that, you need to convert a frequency domain signal to a time domain signal by using the IFFT. So then the time domain signal can be transmitted through the band pass filter. Here, Chibishu band pass filter is used. It can effectively eliminate the ISI and then out of band levels. And then after all these carriers are multiplexed to get the channel, this is our UFMC signal. Then this UFMC signal is transmitted through a channel, wireless channel. Then this is the receiver structure of UFMC system. So first you need to do serial to parallel converter. Then you can employ 2N FFT. The UFMC signal contains the length of N plus L minus 1, where N represents the number of subcarriers and capital L represents the filter length. And then here you need to employ 2N FFT to get the data, effective data. After that, you can use frequency domain channel estimation techniques, equalization techniques to get our signal. And then apply the demapping. That means if you are using FAM, you can use the demodulation, FAM demodulation, PSK, then PSK demodulation, you can apply after that. And finally, you can recover the data. This is the transmitter and receiver structure of UFMC system. Then after completing 5G waveforms, what are the 6G technologies for specially smart cities? Here I have already told you terahertz communication, which can offer 0.1 to 10 terahertz, which corresponds to the wavelengths. Yes, when you're going for the higher frequencies, the wavelength is very less because those are inversely proportional to each other. So here the thing is for 5G and especially for 5G, if the frequency is very, very high, is nothing but you need to go for microcells and picocells to connect, to provide access to all in the area. Then next one is one more technology is optical wireless communication. Optical wireless communication can be operated at greater than 300 terahertz. Why optical wireless communication? Optical communication is different, wireless communication is different. Here we are combining optical and wireless communication. So here, due to the exponential growth of these devices, mobile devices, there is a RF scarcity is there. Your wireless communication technology, the cellular communication is a licensed technology. So RF scarcity problem is there. So to eliminate this RF scarcity problem, we'll combine optical and wireless. Here optical has anonymous bandwidth is there. So the combination, you can take the best features of wireless technology, RF technology, and best features of optical technology. So then you can form a hybrid RF VLC, that is also there. And then optical wireless communication is also better. Then massive MIMO, along with the integration of IRS, intelligent reflecting surface, it provides the good BER. It can reduce the interference effectively. So this combination also provides a better communication for 6G. And then artificial intelligence, yeah, today everything AI dominates. So the integration of 6G waveforms with the artificial intelligence, that means, for example, if you take communications, what are the main research areas is nothing but channel estimation, PAPR reduction techniques to eliminate the nonlinearities and the resource allocation problems. Anything, any algorithm, if we implement with AI, that makes better throughput and reducing latency, reducing overhead. So everything, it is intelligent communication. That's where AI is used. And then UAVs, drone communication is one of the better thing. And then mobile edge computing, this mobile edge computing plus cloud computing and local computing, overall combination of this provides a better services to the users, end users. And then blockchain technology and quantum communication. These are all augmented reality is also one of the 6G enabling technologies. These are all 6G enabling technologies for to get the smart cities will enable these technologies. Then terahertz in 6G, I have already told you, it provides the 6G provides terabits data. Main applications are holographic and massive IoT and VLC, visible light communications. It provides huge bandwidth and ultra high capacity. Applications and technologies, okay, but what are the challenges? This is a very, very important point. So challenges are severe path loss. This is a very, very important thing in wireless communication. And then absorption and hardware non-linearity. So we need to discuss about this one. What are the solutions for this one? So to eliminate this severe path loss, the thing is the solution is channel estimation. And then to eliminate the hardware non-linearities, we need to use a PAPR reduction. PAPR reduction for hardware non-linearities. We need to discuss about this one. And UFMC in 6G, we can use UFMC in 6G also. So the UFMC is still relevant for 6G because it provides better spectral efficiency than OFDM due to the lower side lobe levels. And asynchronous transmissions, there is no need of synchronous transmission here. There is no, not at all required synchronization. And then reduces intercarrier interference, which is very critical in terahertz and VLC bands. So that's why you can combine the RF UFMC waveform with the VLC band. Then it offers, it can offer a 6G communication. Then it can adaptable to combine with the massive MIMO, NOMA. NOMA is nothing but the non-orthogonal multiple access scheme, which is based on the power levels. And then RAS reconfigurable intelligent surface, which provides the better BER, and then with AI aided receivers. So UFMC is adaptable to any system. So we can easily combine with massive MIMO, NOMA, RAS. Automatically it can support the 6G communication also. Then what are the research directions in UFMC enabled 6G systems? That is mandatory thing. So here channel estimation and equalization. We'll discuss about this. And then PAPR reduction. What are the PAPR reduction techniques? Later we'll discuss. And integration with terahertz and massive MIMO, handling severe path loss and beamforming also. AI and ML driven optimization is also. That means intelligent waveform design, adaptive filtering techniques. If we are using filtering techniques in UFMC, if you use adaptive filtering, adaptive modulation, then that is also possible using the AI in UFMC. That is also one of the research direction. Then what is channel estimation? As the name implies, channel estimation. You need to estimate the channel. Why you need to estimate the channel? That is a very, very important thing. Here, wireless communication is nothing. Communication is nothing but transmitter receiver. We are transmitting data to the receiver. In between channel is there. Especially for wireless communication, this channel is not predictive. It is random. It is random in nature. So if it is random in nature, it is not deterministic. It is random in nature is nothing but it is varies. So the analyzation of this, estimating this channel is very, very difficult. So the received signal is usually distorted by the channel characteristics. In order to recover our data original signal, the channel effect must be, you need to estimate and then you can compensate that effect in the receiver. If you estimate it effectively, then you can compensate it in the receiver effectively. Then you can do other operation. Finally, you can get our original data back. This is called as the channel estimation. So how to do channel estimation is nothing but there are three different techniques are there. One is the pilot based channel techniques, and second one is the blind channel estimation, and third one is the semi-blind channel estimation. Each and every method has its own advantages and disadvantages. Out of this, in general, pilot-based channel estimation provides an accurate estimation. So that's why I had taken that part here. So in practical systems, channels are invariably estimated using the periodic bursts of known training symbols. That means we need to give some symbols, then you can estimate easily. Therefore, we mostly focus on these techniques, pilot-based channel techniques. It is simple, accurate, but the thing is, somewhat spectral efficiency is less because the pilot symbols are used instead of the data symbols. So that's why spectral efficiency is less when compared to normal blind channel estimation techniques. And coming to this one, the channel can be estimated by using a preamble or pilot symbols known to both transmitter and receiver. Then only you can analyze, because the transmitter, we are creating the pilot symbols. So known symbols are created. These symbols also known for receiver also. So depending on the arrangement of pilots, there are 3 types of pilot structures are considered here: block type, comb type, and lattice type. We'll discuss about block type and comb type. What is meant by block type? As the name implies here, block by block. So this is one block, this is another block, this is the another block, like that. This is a block type. In this, here the thing is, this column represents the waveform symbol, and these are represents the rows are represents the subcarriers, number of subcarriers. So for example, if you take this one, there are called as the subcarriers. Each and every row corresponds to the subcarriers, column corresponds to the waveform symbol. In this, the symbols with pilots at all subcarriers are transmitted. That is the important point here, where we need to put a pilot. That is important point. Here, this symbol, this dark symbols indicates the pilots. So this is in block type, the symbols with the pilots at all subcarriers. That means if you take one waveform symbol, that waveform symbol consists of all pilots. And after that, there is a block of normal symbols are there. Then again, one symbol consists of all the pilots. So that means these pilots are transmitted periodically. So there is a time this is periodically transmitted for channel estimation. Then how to estimate at the receiver? First, we need to estimate a channel at these pilot symbols. Okay, if you are taking a least squares estimation, H is equal to simply, so y by x, that means known pilots at y divided by pilots at x. So you can estimate easily the channel at the pilot symbol, at the pilot carriers. After that, we need to estimate a channel at data carriers, because these symbols carry the data, these symbols carry the pilots. So you can estimate a data at these carriers by using the interpolation techniques, bilinear interpolation, spline interpolation, low pass interpolation techniques. You can. Here, time domain interpolation is performed to estimate the channel along the time axis. So like that, you need to estimate the channel first at the pilot carriers, then after at the data carriers. So finally, you can estimate all the channels, then apply the equalization techniques to eliminate this one. Then comb type. Comb type is nothing but, in this, every symbol has pilot tones. For example, if you take this one, this is one waveform symbol. That means every waveform symbol contains the pilot tones. That is the difference between block type and comb type. Block type is nothing but one waveform symbol consists of the pilots. So remaining waveform symbol does not contain any pilots. But coming to this one here, the thing is, this is our waveform symbol. This first waveform symbol contains the 3 pilots. Then the second waveform symbol consists of the 3 pilots. And here also, we can transmit periodically. So the statement is, every symbol has pilot tones, because it is every symbol has pilot tones at the periodically located subcarriers, which are used for a frequency domain interpolation. So here also, first we need to estimate a channel at these pilots. After that, using the interpolation techniques, here we are using the frequency domain interpolation, we can estimate a channel at the data subcarriers. So like that, you need to do channel estimation. So this is the pilot-based channel estimation. After estimating channel, if you take a BR, bit error rate, it provides, if you compare the bit error rate with channel estimation, without channel estimation. The with channel estimation offers better BER performance when compared to the without channel estimation. So that is the main thing, channel estimation. It is mandatory for any communication system. Then next one is the PAPR. This is one of the performance metrics of a wireless communication system, especially for multi-carrier systems. So if you take a single carrier system, the PAPR is 0 dB. There is no PAPR. That means the single carrier systems does not suffer from PAPR. That is 0 dB for single carrier systems. But to get high data rates, we need to go for multi-carrier systems. So OFDM is also a multi-carrier system. OFDM also suffers from the high PAPR. In general, the OFDM typical value of OFDM is 12 dB. Okay, so here what is PAPR first? Peak to average power ratio. So as the name implies, it is a ratio of the peak power to the average power. So because if you take a OFDM, we are combining all the signals, sometimes multiplexed all the signals. It can provide a peak power. Some signals have a peak signals. It can take a peak power is very high. So peak power by average power is called as the peak to average power ratio. So what is the problem? If high PAPR is there, what are the problems mainly? A high PAPR requires high resolution A to D and D to A converters. So this is mandatory in communication because entire world is analog in nature. We need to convert an analog signal to a digital converter, and then at the receiver you need to again convert a digital signal back to analog. So A to ADC and DAC converters are mandatory. If you go for high resolution, definitely the complexity is high and overhead is also.
St. Joseph undi ikkada.
Yes, what happened? Excuse me, any?
Madam, no problem. Continue, madam.
Okay. So a high PAPR requires a high resolution A to D and D to A converters, since the dynamic range of the signal is proportional to the PAPR. Yeah. So dynamic range is nothing but there is a difference between small value to a large value. So if you take a normal value, peak value, if it is less, and high peak, that means peak amplitude level is very high. The difference between these two is very high. So the dynamic range of the signal is proportional to the PAPR. So if PAPR dynamic range is very high and PAPR is also very high. So high resolution A to D and D to A converters require additional complexity, I have already told you, and then cost and power burden on the system. So to eliminate these drawbacks, we need to reduce the PAPR. This is a very, very important research topic for multi-carrier systems. And then it can reduces the power amplifier efficiency. So in power amplifier is mandatory. At the transmitter side, we are using the power amplifier. In general, at the transmitter side, the thing is we need to transmit a signal with less power and less bandwidth. Because wireless communication, here there are two primary resources are there. One is the power and second one is the bandwidth. So power should be limited and bandwidth also should be limited. So that is at the transmitter side, you need to transmit signal with less power and less bandwidth. That is the main focus. That's why you are using power amplifier. Here we are using power amplifier to increase the signal strength of a signal. So that's why we need to use a power amplifier, and the efficiency of the power amplifier should be good. But due to this PAPR, there is a non-linearity is there. So the power amplifier operates in non-linear, then it suffers with the non-linear distortions. That is a main problem. That's why you need to reduce. Then the PAPR problem is more important in the uplink, because since the efficiency of power amplifier is critical due to the limited battery power in a mobile terminal. That's why when coming to the 4G technology, in uplink we are using the SCFDMA technique. In downlink we are using the OFDM technique. So because OFDM suffers with high PAPR, so downlink it's no problem. We are using that means there is no battery problems in downlink. That's why you can use OFDM. But in uplink, we can use the SCFDMA. SCFDMA is nothing but single carrier frequency division multiplexes, multiple axis, single carrier frequency division multiple access. That is called as the SCFD-MA. So I have already told you single carrier, the PAPR is zero, almost 0 dB. So coming to this one here, we are using the pre-coding techniques. So we are using something DCT pre-coding, FFT pre-coding, something we are using. So because of that pre-coding techniques, we can reduce the PAPR in SCFD-MA technique. So we are using uplink SCFD-MA in the uplink of the 4G communication system. High PAPR increases the energy consumption, which should be minimum in 6G networks, as energy efficiency is one of the essential requirements of 6G. So energy efficiency is one of the performance metrics of communication system, any communication system, not only 6G or anything. So that's why you need to reduce the PAPR. That is also one of the research area. So what are the different PAPR reduction techniques? So here mainly 3 techniques are there. One is signal distortion technique, and second one is the multiple signaling and probabilistic technique, and the third one is the coding techniques. These are the 3 techniques actually. So coming to this clipping and compounding, this comes under the signal distortion techniques. As the name implies, signal distortion techniques. So that means your signal is distorted. That means your clipping techniques and compounding techniques can reduce the PAPR at the cost of BER. That means the BER is high when compared to without compounding or without clipping, the BER is good. Okay, so here that means there is a trade-off between the PAPR and BER. So we need to careful to do compounding. Then coming to the clipping, it is very, very simple. Clipping is nothing but, you know very well, clip the information. If the peaks are very high, you need to clip that levels. If you are clipping that signal, definitely there is a information loss is there. So you can put a clipping threshold level. If the clipping threshold level is, take a trade-off value between PAPR and BER, it can give a less PR and better BER also. But it causes in-band, out-of-band distortions. To eliminate this one, we will go to the compounding. Compounding, especially as a name implies, compounding. Compression and expanding is there. So that is called as the compounding. Compression plus expanding is called as the compounding. So this compounding offers low complexity and performance loss by compounding. It is also suffers from compounding loss, but it okay depending on the parameters. Compounding parameters are there. For example, if you take a Mueller compounding, Yela compounding, and then exponential compounding, there are many compounding techniques are there. If you take a Mueller compounding, especially for UFMC technique, if you take a Mueller compounding, if you take mu is equal to the value of Mueller compounding is it starts from mu is equal to 1 to mu is equal to 255. So if you take a mu is equal to 1, the PAPR is something, let us assume the PAPR is around 8 dB, let us assume 10 dB. If you are using mu is equal to 5, the PAPR is almost 6 dB or 6.5 dB like that. If you go for mu is equal to 10, mu is equal to 15, it offers better PAPR performance. That is less low PAPR. But coming to the BER, when you are increasing mu value, the BER performance degrades. That's why you can take a trade-off value. For example, if you take a mu is equal to 4, it offers maybe mu is equal to 4 is nothing but it offers maybe a 6 dB PAPR, and bitter rate is also very good. You can take that value. That means there is a trade-off value you need to take. So like that, you can reduce that signal distortion also. So the signal distortion techniques are have a less computational complexity, but little bit distortion is there. Coming to the selective mapping and partial transmit, these come under the multiple signaling and probabilistic techniques. As the name implies, probability here, these can provide the high complexity. It requires a side information also. So we are using phase rotation, phase shifting techniques. We are using those techniques to reduce the PAPR. And we need to select a signal with minimum PAPR. So that's why high computational complexity is there. But there is no problem for BER. Bitter rate is good. There is no signal distortion here. The thing is, we need to give a high computational complexity, and side information is also needed. That means complexity is very high. So coming to the encoding techniques, it requires more bandwidth. That is also, it is also provides less PAPR, but it requires more bandwidth. So each and every method has its own advantages and disadvantages. Depending on the application, you can choose the technique. Then, so those are the research areas. And then coming to the performance indication between this 5G and 6G. For example, if you take this one, parameters, the peak data rate, this is very, very important, because when you're moving from one generation to next generation, the data rate increases. Okay, so data rate is nothing but we are transmitting data. Okay, so the 5G offers 20 gigabits per second. It is expected, but generally it offers 10 gigabits per second. And coming to 6G, the expected is 1 terabits per second. Maybe you can get around 50 gigabits per second. Okay, after implementing. So experienced data rate is 0.1 gigabits per second and 1 gigabits per second. So spectral efficiency. So spectral efficiency is very, very important thing. So as an name implies, spectral efficiency, because the cellular system is a licensed technology. We need to buy a spectrum. That's why spectrum you can use effectively. So whatever the allocated spectrum is given, you need to use effectively. So then it is called as the spectral efficiency. So peak spectral efficiency is 30 bits per second hertz, and here 60. So spectral efficiency of 6G is very high, expected. And then experienced is 3 bits per second, and maximum bandwidth is 1 gigahertz. And for this one is 100 gigahertz. So more bandwidth is nothing but you can transmit more and more data. So because of this bandwidth only, you can get a more data rates also. So area traffic capacity, and then this is 10 megabits per second per meter square, and then this is 1 GB per second. So area traffic capacity is also, that means it can provide a more capacity. Connection density is nothing but I have already told you, massive machine type communication. So that due to that massive machine type communication, more devices, that means 10 power 6 devices per square kilometer, you can connect the devices. And then here 1 terabit devices you can connect. And then energy efficiency for this one is it is not exactly specified, somewhat less when good energy, better energy efficiency when compared to 4G. And coming to this one is 100 microseconds. And reliability is high, 1 to 10 power minus 1, but here 1 to 10 power minus 9 reliability is there. Jitter is nothing but delay around, it is less than 1 millisecond, but exactly not specified, but it is less than 1 millisecond, here almost 1 microseconds. And mobility, here mobility is very high, because number of devices are very, very high, and urban environments are comes into the picture. So mobility is also very high, and we need to tackle this mobility also. Yes, our title is 5G or 6G communication systems. Until now, I have discussed about the little bit 5G communication, that is UFMC system, and then 6G, some technologies, digital twin technology and holographic applications are there. And I have discussed about the research areas, channel estimation and PAPR. Then smart network management. So smart network management is nothing but we need to, for example, if you take a home, whatever the appliances are there, everything we need to operate in a smart way. So to operate the devices in a smart way, we need to add some intelligence to that devices. So that intelligence is possible due to the artificial intelligence. But as the name implies, frankly speaking, it's an artificial intelligence. So everyone, I think you know that artificial intelligence is nothing but it is a neural network. For example, neurons. But artificial intelligence, it's an artificial, it is not human intelligence. Human intelligence is very powerful when compared to artificial intelligence. But what are the machines we have already created for the sake of our safety, our convenience, and then security purpose, and then we can operate thus the machines, we are created that machines, we need to add intelligence to that machines. That's why we are using the artificial intelligence. We are adding artificial intelligence to our devices. Then it makes a smart home. Like that, smart city is nothing but you need to add a smart devices to your mobiles and street lights, everything to be smart. Then it is called a smart home, smart cities, smart, everything to be smart. Then what are the challenges? So here the challenges, what are the challenges need for this intelligence? So wireless network challenges. Modern wireless networks struggle with latency. Yes, because if you want to download movies or anything, the downloading speed and upload anything is nothing but the speed. Okay, still latency is there. Then energy inefficiencies are there. Spectrum scarcity, I have already discussed RF, because RF communication, there is a scarcity is there. We need to address that problem also. And scalability issues due to the device growth. These are all problems due to the device growth. AI and machine learning solutions. This AI and ML enable dynamic resource allocation. Yeah, the main thing is resource allocation. Resources. What are the resources for channel communication is nothing but power and bandwidth. So resource allocation is the one of the major research area for 6G communication. This resource allocation, already resource allocation algorithms are there. That resource allocation algorithms is controlled by this AI, because if you are using a dynamic resource allocation algorithms along with adding artificial intelligence, it can reduce the spectrum scarcity. Then we can increase, because power allocation algorithms are there and bandwidth allocation algorithms are there. So based on that, we can get the energy efficient systems and also spectrum efficient systems also. So that is the beauty of adding a artificial intelligence to resource allocation schemes. Then traffic prediction. We can predict the traffic because number of mobile devices increases is nothing but depending on the traffic, we need to give access to the mobile users, because customer satisfaction is very, very important. Here, depending on the dynamic traffic, we can give access to the mobile users. That is also possible due to the AI and ML, because it can take the dynamic, it can take the real data and it can give the perfect decision, because AI or ML is nothing but they can train the system million times, they can work and it can give accurate data. So depending on that accurate data, we can give the access to the mobile users. So that is possible due to the AI. And then detection of network anomalies for better management. That means maybe a network issues, any network issues also it can measure depending on the environment issues or anything. So then based on this real, that means dynamic data, we can take a proper decisions due to the add of AI. Then benefits of smart network management. Smart systems optimize operations in real time, reduce energy consumption, and enhance security, and then safety, everything. It can comfort also. So smart home is mainly based on comfort. If you want to get good comfort is nothing, you can make your home to a smart home. That is possible due to the AI only. Then role of AI in network optimization. Yes. If you take this structure here, interconnected lines and nodes are there. Here, interconnected lines, these are called as interconnected lines. These symbolize the massive decentralized data flow. Yeah. So in 6G networks. So massive is nothing but more number of devices. Okay. Here, many things are there. Not only devices, there are devices, sensors, edge servers, okay, cloud, many things are there here. This figure symbolizes many things. Mainly, first one is interconnected lines and nodes. So these interconnected lines symbolizes the massive decentralized data flow in 6G networks. 6G, we can connect more devices, more than 1 lakh devices we can connect it. So that is shown here, and then color coded nodes. Here there are color coded nodes are there, may represent the different types of data sources, that is devices, sensors, edge servers. So we can use, and these peaks indicates what is this peak. Sometimes valleys are there. So these peaks and valleys indicate the real-time fluctuations in network traffic. Okay, so sometimes the traffic is, if you take a busy hours, the traffic is very high. Here the traffic is nothing but mobile traffic. So during that time you need to take a more care. So you need to give access to satisfy every user. And then it indicates the signal network traffic, signal strength, or resource allocation also. And then dark background with bright lines. Some bright lines also there here, dark background. So these indicates, highlights the contrast between raw data and intelligent processing. That means AI brings clarity and structure to a complex systems. So here mainly AI, we are discussing about AI something, machine learning, and here deep learning is also one of the important technique, and this reinforcement learning is used in many applications. If you take, for example, every time we are watching YouTube and Instagram, many reels or something, here there is recommendation algorithms are there. So recommendation algorithm, that means we are getting some recommendation. For example, if you want to browse only education related data or related to communication data, I'm browsing only communication related data, then I can get only the reels or something, the videos based on that thing only. That means I can get a recommendations only about that data, or I'm going through any type of data, it will give only recommendation. So in that recommendation algorithms also depends on this reinforcement algorithm. Based on this reinforcement algorithm only, they are designed. Like that, in every thing, we can use this deep learning techniques and reinforcement learning techniques. And conventional neural networks improve wireless network performance and security also. So 6G network integration, AI embedded in 6G networks allows self-learning and self-optimization for autonomous management. Then applications in optimization, AI enables intelligent routing. So coming to the routing is nothing but we can transmit data from one node to another node, because here the thing is OSI layer. OSI layer is nothing but it consists of 7 layers. Physical layer, we can use this OFDM waveforms and that UFMC and FDM access, multiple access schemes, NOMA, you can use everything. And coming to the data link layer, we are using the error control detection. MAC layers are there, MAC algorithms, you can do it. And coming to the network, there is a routing is there. So here you can provide intelligent routing, adaptive modulation techniques, and real-time decisions in wireless resource allocation. Then IoT integration in 5G or 6G networks. So IoT, as the name implies, IoT, Internet of Things, that means the physical objects connected together. So as the name implies, IoT, the physical objects is nothing but the IoT device consists of the sensors. It can take the data and then it can process. It can contains the processor because it can process the data, and then it consists of the wireless communication device. So for that wireless communication, again you can use that UFMC or OFDM, NOMA. So that technology, you can use wireless communication technology to provide access to the multiple users, and then actuators. So this is the combination of IoT. So with the integration of IoT to our 5G networks, what happened, we'll see. So this is the use cases. This is the IoT architecture components. So again, smart. So IoT architecture includes edge computing, cloud integration, and intelligent gateways for seamless device communication. So everyone knows about cloud integration and cloud computing. Cloud computing is nothing but Amazon Web Services, AWS, and Google Cloud also there. So cloud is nothing but it is many business people, they can use that. They can save that data, store the data into the cloud, and it can perform computing. But the problem of cloud computing is the overhead is very high, and also delay is also very, very high, because we need to transmit data. End users can transmit data to cloud. It will take a lot of time. So that's why, so we can put a edge devices, that is called as the edge computing, mobile edge computing. You can put a edge servers near end users. Near end users you can put. So automatically you can, instead of sending data, a normal application data can transmit, a end user can transmit to a edge servers. Then this edge servers can compute, process, or can perform computations effectively when compared to the local computers. So that's why the delay is reduced. Then that is called as the IoT ARCTE. That is the one of the application. And then diverse use cases. IoT supports smart cities, healthcare monitoring. So because especially in healthcare monitoring, we are unable to diagnose the problem first. So some people, in the last case, you can detect cancer, and then heart attacks, something like that. So if you are IoT, along with that digital twin technologies, we can make a smart healthcare monitor. We can diagnose easily and so, and then industrial automation. So industrial is nothing but they need to provide more and more service to the users. That's why here also we need to use IoT devices. Agricultural enhancing. So industrial IoT is also one of the better area, industrial IoT. So that means when you come into the agriculture area also, so if you want to detect any something happened, whatever happening is there, you can put some IoT devices. It can sense the data immediately. Based on that data, we can take the decisions. We can optimize. And then evolution to intelligent IoT. 6G enables intelligent IoT where devices analyze and act on data autonomously for applications like robotics and predictive maintenance. So this is about the architecture and use cases. Then AI IoT synergy in smart networks, the combination of these two. So AI and IoT synergy, AI enhances IoT by analyzing the devices to learn and adapt in real time. And what are the applications are? The AI IoT synergy enables autonomous vehicles, smart manufacturing, and digital twin technology is also based on this AI IoT. If you combine a 6G technology with AI and IoT, if you take IoT, let us assume IoT, you can use edge computing is one of the technology for IoT. You can combine this mobile edge computing with the AI, then it is called as the edge intelligence. That's edge intelligence perform computations effectively when compared to the normal edge computing. That is called as the AI and IoT synergy. So IoT comes to the edge server. Let us assume this is the IoT device, that's the edge server. Okay, it can perform a resource allocation and also computations. But coming to the adding intelligence, that is artificial intelligence to the edge, then it is called as the edge intelligence. So when compared to normal edge computing, this edge intelligence gives a better computation, and that means overhead is very less, and perform computations effectively. That means less delay. Delay is very, very less. It can perform immediately, and then it provides a better resource allocation algorithms. That is possible due to the AI IoT synergy. Then advancements with 6G networks. So that means you take edge computing plus IoT. This is called as edge intelligence. You can add 6G network to this edge intelligence. What happened? So 6G networks enhance real-time processing and edge computing for faster and accurate decisions. So benefits of AI IoT integration. This enables smart, responsive, and efficient networked environments. So this is called as the AI IoT synergy provides these applications. Then edge computing and network slicing. So main importance of edge computing, because edge computing is the 5G technique only. So for this edge computing, if you add an intelligence, then it is called as it comes to the 6G technology. So low latency and service customization is the very, very important thing for edge computing. So the edge computing reduces the latency by processing data near the user. I have already told you. So near the user, you can, Yeah, near the user, you can put a edge server instead of transmitting a user, instead of transmitting data to the cloud, they can transmit data to the this edge server. So the delay is very less. Automatically, it can perform effectively by adding the intelligence. So it enabling faster real-time applications. Then network slicing functionality. Network slicing creates a virtual networks customized for specific applications to optimize the performance. So network slicing is nothing, it can provide it can create a virtual network. So we can easily optimize that. Then use cases in 5G and 6G technologies enable diverse uses like remote healthcare, immersive gaming, and industrial automation you can use. So AI integration in 6G, AI with edge computing, I have already told you, that is edge intelligence for intelligent data processing and dynamic service delivery. Then real world applications of AI and IoT, sector-wise implementation, that is healthcare monitoring. AI-enabled IoT devices monitor patient vitals and enable remote diagnosis. So improve this efficiency, and it can provide a comfort to the patients and also for doctors also. They can easily diagnose the problem. And then transportation innovation, this is very, very important because the traffic is very, very high. So we need to handle this one also. So autonomous vehicles use AI for navigation, supported by IoT sensors, providing real-time traffic data for safer travel, and also to provide intelligent transportation system also. Security purpose also. So this is also possible due to the AI enabled with IoT devices, and then 6G networks. Then education technology, immersive AR, VR learning experiences are supported by low latency networks, enhancing education through technology. Definitely. So this technology is a two-edged sword. One side, due to this technology, at our home, the world is with ours. So we can learn anything by using this technology. So education perspective, if you are using effectively, the not only student, faculty are also benefited. So everyone is benefited using this one. And then enhancing education through this technology. Then industrial automation, so predictive maintenance and intelligent robotics powered by AI and IoT boost efficiency in industrial operations. So that means, so in manufacturing units also, if we add intelligence, then you can easily identify that any problem in that manufacturing units, and also we can easily identify the problem, and then we can, that means if you identify the problem effectively, then we can reduce the any problems. That means sudden industrial explosions are there, so we can reduce that problems also. Challenges and future directions. Yeah, what are the research opportunities? This is a very, very important for faculty side. So major deployment challenges, spectrum allocation. So this is very important, spectrum allocation. Then energy consumption, that means energy efficiency, and security vulnerabilities, that means network security. So for this one, you can use the quantum security. You can use quantum communication and quantum security. So remain significant barriers to 5G and 6G deployment. And then AI native network infrastructure. So deploying AI native networks requires robust infrastructure and careful ethical considerations to ensure reliability and fairness also. And then research and innovation opportunities include energy efficient protocols. You need to design enhanced data privacy, network architecture for future wireless communications. Collaborative, that means we need to collaborate with the industries and government because to get a projects also. So these are the trending topics. That means if you that means edge intelligence along with NOMA technology, and something quantum communication, quantum technology with the artificial intelligence. These all are the we can write a projects also. We can apply projects and collaborate with the academia industry. This is essential for testing standardization also. And then coming to the conclusion. So wireless networks I have started from 1G voice. Then the technology now comes into the 6G intelligent connectivity. Then 5G introduced a massive MIMO, millimeter wave, and early UFM's adoption for flexibility and low latency. And 6G pushes the boundaries with terahertz communication for TB, that means terabits per second data rates. And advanced UFMC, that means UFMC is already discussed for 5G. And if you want to get advanced UFMC for massive IoT and ultra reliable low latency and spectrum efficiency, you can add some intelligence to that UFMC. Integration with AI, RIS, reconfigurable intelligent surface, and edge computing for intelligent and adaptive networks. So the challenges remain are you need to do channel estimation at terahertz, it is mandatory, and PAPR reduction for reducing the nonlinearity in the power amplifiers and LED devices. If you take a VLC also, visible light communication, that is also one of the application for 6G networks. If you go for VLC, you can use LED and VLC. It is called as a visible light communication. So visible light communication, you can use the LEDs and lasers. So LED is again, there is a non-linearities in LED. So to eliminate that, because of that thing also, the PAPR, to eliminate that thing, we can use a PAPR reduction techniques here also. Then future outlook. So not only FMC, you can go for NOMA or massive MIMO, anything UFMC plus artificial intelligence and terahertz communication. That means 6G technologies. Key enablers for 6G applications like holographic communication, digital twins, and pervasive IoT. So with this, I have concluded. Any queries?
Thank you, madam, for your valuable insights and
Yes,
providing valuable knowledge, madam.
thank
On
you.
behalf of EC department, we appreciate the effort you put into the making the content relevant and impactful, madam. Thank you, madam.
Okay, sir. Thank you, sir. Thank you, sir, for giving this opportunity. I'm also delighted here because I'm also part of this FDP. Thank you so much, sir.
Dear participants, if you are having any queries, means we can clarify with our resource person, madam. Or else you can put the queries in the chat box. Dear participants, if you are having any queries, means you can ask the resource person. Okay, madam. I hope there are no.
Okay, sir.
You can leave, madam. Once again, thank you very much, madam, for your valuable. Thank you, madam. Have a nice day, madam.
Thank you.
Thank you, madam.
Thank you, sir.
Okay, madam.
మహబూబ్ బాషా
సార్
ఆ ఫీడ్బ్యాక్ లింక్ ఏమైనా షేర్ చేయగలవా?
పంపిస్తాను సార్. ఉంది సార్. ఎస్ సార్, నా దగ్గర ఉంది సార్. అదే సెషన్ అయిపోయింది.
ఓకే.
మేడం లిఫ్ట్ అయిపోయిన తర్వాత పంపిస్తాను సార్. Dear participants, feedback link is kept in chat box. You please try to complete the feedback link as early as possible. It will be available for few minutes only. You please fill the Google form as early as possible. Dear participants, those who have not filled the first session, please fill the feedback. It is available now. Dear participants, those who have not filled the feedback links, please try to complete as early as possible. The feedback form is available in Google chat box. The session will be winding very early. Dear participants, those who have not filled the feedback form, you please complete the feedback form as early as possible.